Hi, this series of lecture will be on buckling. Okay, so the first thing we have to understand is mechanical properties. So how does mechanical properties relate to stiffness of structure? Okay, so we have to look into this first. So under compression axial loading, so I deliberately selected compression because buckling will only occur in compression loading. Okay, you not get buckling in tensile loading. So if we have a structure now under compressive loading, so one end is built in, so this is our structure, and we have a load, and this load is P at this moment of time is equal to 0, and over here we have our A, which corresponds to our area. Okay, so we know from here we can easily write down that stress is equal to minus P over A. Okay, we can easily write this down. And then with the structure being compressed, so the next mode, now the structure is under a certain load. Okay, so on top is lock-in, and then it's been compressed. Alright, so over here now the structure is under compression. Over here where P is no more equal to 0, so what we have now, originally we have our length. Okay, so originally we have our length from here to here, so this is our L0. So now after axial compression, our load now, our length now become L1, and we know that the distance from here to here is our delta L, right? So applying looking at Hooke's law in the elastic region, we are also aware that this is, I'm going to draw the linear stress strain relationship because we're in the elastic region. So epsilon normal stress, so we have a relationship when the elastic region, we have a linear relationship, and what we have over here, the slope over here is equal to E, and this is in the elastic region. So we are aware that in the elastic region that stress is equal to E Young's modulus multiplied by epsilon. So this is my equation 1. So this is what we normally call Hooke's law, and we are aware that the strain in the y direction, like what we've just drawn. So if I draw my transformation, this x and this is y, is equal to delta L divided by L0. So this is our equation 2, and then this is our equation number 3, right? So we know that the strain is under compression, so the change will be negative. So we're going to substitute equation 2 and 3. Okay, 2 and 3 into equation 1. Okay, so we have minus P over A will be equal to Young's modulus minus delta L over L naught. Okay, so if we rearrange this, we have the change in length is equal to P L naught divided by AE. Okay, so this formula should look really familiar to all of you now. So from here, so this is my equation number 4. Now this is only true is where you have the elastic region, right? In the elastic region where we have a non-buckling situation. Okay, the axial loading is not high enough, the compression axial loading is not high enough to induce buckling. Okay, so remember how we started is we want to relate this to stiffness of the structure. So let's define what is stiffness first. Okay, so let's look at stiffness. So we can see that if we draw our axis now, alright, so what we have over here, we have y, we have p. The higher you want to deflect the structure, the higher load you want, and this gradient over here is your K. Okay, so K, so we know that this is meter and this is in Newton. So K over here, small k, is defined as the stiffness, which is in Newton per meter. Okay, so how much Newton, how much force you need to increase the length per distance, how much force is required to stretch a meter of elongation. That's called stiffness. So P is equal to K multiplied by Y. Okay, so Y over here will denote the deformation. So what we have, that the change in L, okay, is in fact equal to Y. So this is my equation number 5 over here. So we can let equation 4, okay, we can let equation 4 let equation 4 or equate equation 4 and 5. Right, by using this relationship. So delta L is equal to P L naught over AE, and this is equal to, so by using equation 5, so it's equal to P over K. So you get rid of P, so what you have is L naught over AE is equal to 1 over K. And we know that K, stiffness, is equal to AE over L naught. Right? So this is our equation number 6. So from here we can see that the stiffness, right, the higher your or larger your area and Young's modulus, you have higher stiffness. If you have longer L naught, the stiffness will be reduced. So however, unfortunately, in buckling situation, Okay, equation 6 is not valid. And why is not valid? Because the deformation in buckling is not parallel to the axial direction of the structure. Okay, so in order to go into buckling, you have to go into Euler's formula applied to buckling. Okay, so let's look at buckling, and we have to look at the deformation pattern. Okay, we have to go into the deformation. So let's consider deformation pattern for buckling. Okay, I'll go. Okay, so we have to apply Euler's. Okay, so let's look at deformation pattern. Okay, deformation pattern during buckling. Okay, so during buckling. So what we tend to have, as I mentioned before, we tend to have a structure. Okay, that one end is usually built in, and at the other end you have a load P0 or just P, and then you have a overall length of L0. Okay, so this is your overall length. So the deformation pattern, if we now were to sketch the deformation pattern, okay, so I will have my axis over here. So this will be I will use a different color. This will be my x-axis, right? Sorry, this will be okay. I'll call it y for now. Okay, I'll call it y, and along this length, this is my x-axis. Right. So the deformation pattern, by looking at the neutral axis of the structure, this is the deformation pattern. Okay, so this is the deformation pattern. So at the top point, where x is equal to 0, y is also equal to 0, where x is equal to L, y is equal to 0. Okay, so our load P has been still applied down here. Okay, and then if we pick any point Q, if let's say we're going to pick a point over here. Okay, so this is my point Q. So we have a distance from here to here. This will be my x value, and then we have another value over here. Okay, so eyeball approximately, and this will be a y, right? So the deformation that you see down here. Okay, so the deformation pattern that you see is similar to those induced by bending moment. Okay, so it's similar. So what do I mean by that? So if I draw at a point, okay, if I have a point down here, so in terms of axis, this is 0, 0, and then we reach point Q. So this is our point Q. Your deformation looks like this, right? So that is how your structure deform. Okay, and this is our point Q. So what you see over here, we know at 0, 0 point, right? At 0, 0 point down here. Oh, sorry. At 0, 0 point, I'm trying to get rid of this dot over here. No luck. Okay. So at the 0, 0 point here, right? So X and Y, Y and X, you still have the load coming down here. So this is still our P, right? So our P is still going down in the X direction, right? So we have at point Q, we have action equal to reaction. So you have at point Q, you have a reaction over here, P, right? So if you were to put your fixed point at point Q, point P will induce a anti-clockwise direction rotation. So over here, the moment at point Q. Okay. So this is how at point Q you get your you have your reaction. Okay, so I'll put P down here. You get your reaction. So moment about point B. So we know that the distance, we are aware that the distance from here to here, we know this distance is y. So we are aware that moment about point Q is equal to P multiplied by y. Okay, we are aware, and it's in the clockwise direction, so minus P multiplied by y. Okay, so moment about point Q, right? So we have to apply, or we can apply the elastic curve equation, okay, to relate bending moment, okay, bending moment to deflection. We learned this last week, right? So we know that M moment is equal to EI d squared y over dx squared. This we are aware. Okay, right. So this is what we apply the elastic curve equation. Okay, I'll come back again.